Let's continue our analysis of the resistive force model in AP Physics C. So we're going to start with this situation that was introduced at the end of the last video about this, in which it was just introduced. So either a bullet being shot into a gel block, or a situation like this box being given an initial kick to give it some initial velocity before it then slides across a frictionless surface and gradually slows down due to drag with the air. Doesn't matter which one you choose. In either case, we start with a force diagram. So we're going to have a downward force of gravity, Fg. We're going to have an upward normal force supporting it from below. These are going to balance out. They're not going to actually influence our analysis at all. What's going to actually influence our analysis is the Fr, the resistive force. I made it going to the left because our objects both have velocities to the right. If our objects had velocities to the left, this resistive force would be going to the right. If our objects had velocities going up, this resistive force would be going down. So that means that the resistive force is our net force. And so that means, well, we know that net force is equal to ma from Newton's second law. I'm going to drop the vector symbols because they start to get kind of annoying. But of course, you know that a is a vector and v is a vector. And then the resistive force is negative kv, as we discussed. Remember that k value is going to be based on the size and shape of the object traveling through the fluid, as well as the density of the fluid. So now what we want to do is, this a is equal to the time derivative of velocity. And we've got velocity there, and we've got the time derivative of velocity there. So I'm going to rewrite that as the differential. And this differential here makes this a differential equation. So now what we're going to do is get rid of the m, move to the other side. dv dt is going to be equal to negative k over m times v. So now that we've got our differential equation with an isolated differential, we need to figure out, how are we going to solve this thing? The most basic method of solving a differential equation is called separation of variables. And it involves exactly what it sounds like. We're going to separate our variables. So we've got a v and a v. We want to get all the v's on one side. And we've got a t here. We're going to get that onto the other side. So we're going to divide this term over here and multiply this term up to there. So we get dv over negative k over mv is equal to, I apologize, we don't need to actually move that whole thing. We're just going to divide the v over. There we go. That's much simpler. Negative k over m dt. Next, we can integrate, because what we're actually looking for here is from this analysis is an equation for velocity as a function of time. In order to get that, we need to get rid of this dv. We also want to get rid of that dt, so we can actually have t in our equation. So we're going to integrate both sides. Now, this is just going to be a natural log. If you look at your equation sheet that goes along with AP Physics C, you'll see dx over x integrates to natural log, or you may know that from calculus. On this side, well, the k and the m, along with the negative, are all constants. So I like to take those out of my integrals. So I would actually rewrite this to have the integral symbol here. That way, I'm just integrating dt. These constants can be pulled out. So I get the natural log of v is going to be equal to negative k over mt. Now, at this point, you may be questioning, well, why didn't I put a plus c on each of these? I can. So let's say I do plus c1, and then here I do plus c2. So in this situation, I've got two c's. There's no need to have two c's, because what I could do is just subtract this c1 over to the side, minus c1, get rid of that. And now this, I could just call this c. C is just an arbitrary constant. It doesn't actually matter what it is. So that's what I'm going to do. I'm just going to have a big C right here. And that C takes care of the C from this integration and that integration. Okay, so now I don't have any differentials in my equation anymore. That's a step in the right direction. However, I need to get that v out of the natural log. So how do you get a v out of a natural log, or how do you get anything out of a natural log? You exponentiate. So we're going to exponentiate both sides. Now, why are we going to exponentiate? Because e to the x is the inverse function of a natural log of x. So if we do e to the power of natural log of x, well, that's just equal to x. Or if we do the natural log of e to the x, that's just equal to x. So that trick will get our v out of its prison. However, if we exponentiate this side, we have to exponentiate this side, as always. So let's go to the next page. So we had here the natural log of v is equal to negative k over m t plus c. Let's make sure that's correct. Negative k over m t plus c. Good. So now we're going to exponentiate both sides. So when I e and then e, so these cancel out. Well, they're inverse functions, so they're going to go away. We're just going to end up with our v. And we're going to, on this side, have e to the negative k over mt plus c. Now, here's where we can use some of our exponent rules. If we have, let's say, 2 to the power of x times 2 to the power of y, well, we know it's equal to 2 to the power of x plus y. So what we're going to do, or we could, another way, maybe this is more familiar, 2, or x to the power of 2 times x to the power of 3. Well, that's equal to x to the power of 2 plus 3. Right? That's x times x. This one is times x times x times x. Well, that's 1, 2, 3, 4, 5 x's. Right? 2 plus 3. So it works the same way if the variable is in the exponent as it does if the variable is the base. So we can change this to be e to the c times e to the negative k over mt, and that's all equal to v. Now here, this is e to the c. E to the c is just going to be a constant as well. So I can just call e to the c, c again. Because again, this c is just a placeholder for any constant value that is lingering around through our math. So now this looks a little bit nicer to work with. And we pretty much have an equation. So this is velocity as a function of time is equal to c e to the negative k over mt. Great. But now we need to figure out what c is. To figure out what c is, we use our initial conditions. So our initial condition would be that at time t equals 0, v is equal to v naught at t equals 0. Or we could say v of 0 is equal to v naught, whatever the initial velocity is. In the case of the bullet hitting the block, it's how fast the bullet's going when it hits the block. In the case of a box that's been kicked and then slides to the right on a frictionless surface, it's how fast the box was going immediately after the kick. So then we can say, well, our velocity is going to be 0. Our velocity is going to be v naught at time t equals 0. So I'm going to plug in a 0 for t. So that negative k over m times 0 is 0. It's going to be equal to c e to the power of 0. Well, e to the power of 0 is 1. So c times 1 is just c. So c is equal to v naught. So that means we can rewrite this as v as a function of time is equal to v naught e to the negative k over mt. And that's our equation. Not too bad. So what would this look like if we were to graph it? Well, just looking at this, immediately we see this is exponential decay because there's a negative sign in our exponent. So the way that exponentials work, and they're going to cross at whatever the value, they're going to cross the v-axis in this case, at whatever value you get when we plug 0 in for t. In this case, that's going to be v naught. So we're going to have v naught there, and that makes perfect sense because that's how fast the object's moving at time t equals 0 when we start our timer. In the case of the bullet, when it makes first contact with the block. In the case of the block sliding across the floor, when it first leaves your foot after you kick it. So then this term is going to be an exponential decay, which is going to be this. You're going to asymptotically approach 0. For any practical purpose, this does actually reach 0, right? When this thing is moving at 1/1000th of a millionth of a nanometer per billion years, that's stopped for any sort of practical purpose. And in reality, it will be stopped because there will be various other factors at play. This equation is still somewhat idealized. But mathematically speaking, it asymptotically approaches 0. And that it being velocity or speed in this case. So that's what that graph would look like. And you can check yourself in a graphing calculator. Just decide, maybe you want your V0 to be 10 meters per second. Maybe you want your K value to be equal to 1, and maybe your mass also equal to 1, just to simplify things. If you want to change those up, though, you can see how changing your K and your M would alter your graph. It's not going to change the general shape of the graph, but it will change maybe how long it takes for it to start to really approach 0. And of course, changing V0 will change where you start. So changing K, remember, that would be like having a denser fluid. That would be like having a less aerodynamic shape of object, or having a object with a larger surface area. And that was for increasing K. For increasing M, that would just be making a more massive object. So I'm sure you can imagine if you increase M, it'll actually take it longer to slow down because the object will have more momentum. But in the context of AP Physics C, if you're watching this along with the course, you haven't gotten the momentum yet, so that might not mean too much to you. But I'm sure you've heard that word before. Probably have some basic idea of what it means. So if I were to do that, if you're using a T89, you can follow along perfectly on this calculator. If you're using a T84 or some other calculator, it's the same basic idea to graph something. We don't care about the specifics of this calculator. We care about what the graph looks like. So we said V0 is equal to 10 times E to the negative. Well, this is going to be 1 over 1, so I'm going to ignore that. So negative T, so I'm just going to type in an X there instead. And then let's see what the window should look like. We don't need negative time. The x-axis is time. We'll start our time at 0. We can go to 10 seconds. That's fine. For the position, for the velocity rather, we're not going to have negative velocities. We define this to be positive velocities. And we'll see what, well, our initial velocity is 10, so that's actually a pretty good maximum. So we'll see how it decays from its maximum value. And then we'll graph. And there you go. You can see we started at 10. And then in this case, we pretty rapidly slowed down. Now, if I were to do this again, let's do 10e to the, let's say mass is 2 this time. So if mass is 2, k over m will become 1/2. So I can use 0.5x or 1 divided by 2 times x. Either one would be fine. And then you can see or not. What did I do? Oh, I forgot to put the negative in there. Now you can see exactly how increasing the mass would change the shape. Notice that once it finishes graphing that one, look, it takes longer for this thing to slow down because there's more mass, which is going to resist the resistive forces more because it has more inertia. So that's terminology, rather than using momentum, that's terminology that at this point you should understand. By this point you should know Newton's first law pretty well. So more mass means more inertia, means more resistance to changes in motion. So it's going to continue its motion more effectively with more mass. And if we increase the k value, it would slow down faster. So there you go. that is finding the velocity time equation for an object experiencing a net force equal to the resistive force. In the next video, I'm going to go over how to get the acceleration and position equations for this object.